Hello class, this will be the second half of 4.3 dealing with logarithmic functions. As you're watching these videos, I might go through a couple things a little fast, but feel free to stop, pause, back up, whatever you need to do to make sure you get through all the notes, because I want to make sure that the videos stay at a length of around 5 to 8 minutes, somewhere in there, no longer. So feel free to stop at any time. So for a warm-up, write the inverse of this function in logarithmic form. So we know this function is going to be simply y equals 2 raised to the x power. So therefore the inverse is 2 to the y. Well, we can write that as a log of base 2 of x equals y. Second part, what is the domain of an exponential function? Well, we know a general exponential function looks like that. And so our range is going to be from negative infinity all the way up to positive infinity. And because a log function is an inverse, the domain of our exponential function is negative infinity to infinity. Our range of our inverse will be the same, negative infinity to infinity. Because remember, they switch. The domain of an exponential becomes the range of a logarithmic. The range of an exponential function becomes the domain of a logarithmic. Okay, so this one on the left, this is things that we've seen already. So these are just general characteristics of an exponential function. Well, now let's look at the characteristics of a log function. So it's going to be very similar. If your a value, your base, is greater than 1, f is an increasing function. If it's between 0 and 1, f is a decreasing function. Now this one, the points, because it is an inverse, you can see these points are opposite or switched x and y values. So those points on the right will lie on the graph of an exponential function. The points on the left are what's going to lie on an exponential function. For a log function, now y is the horizontal asymptote. And the domain, again, these are switched. So the domain of a log function is 0 to infinity, and the range is negative infinity to infinity, which is just going to be the switch of each of these. If we were to look at these graphically, because it's an inverse, it's going to be reflected across the line y equals x. Our red line here is log base 2 of x. Our blue line is y equals 2 raised to the x power. And we can see on the left our table of values. So our blue line, 2 raised to the x power, that's an exponential function. We know it's going to go through the point 0, 1. Well, in the inverse, the log function is going to go through the point 1, 0. Okay, and we can see all these points are reflecting over this line y equals x. We can do translations when working with log functions as well. So if I had just over here log base 4 of x, and then I have log base 4 of x plus 1, cut off that plus 1, but this is log base 4 of x plus 1. We know in our parentheses that x plus 2 actually shifts left 2 units. And then the plus 1 shifts up 1 unit. So we can see our original function. This is the log base 4 of x in the purple. And this is log base 4 of x plus 2 plus 1. So we can see our point here at 1, 0 for our log base 4 of x is shifted to a negative 1, 1. Okay, what happened? It shifted 2 units to the left, and then it shifted up 1 unit. Same thing with this point, 2, comma, 0.5. It shifted left 2 units, so now it's on the y-axis, and up 1 unit. Next, we'll go over some properties of logs. So these are ones you've seen before, but I'm just going to run through them. You can pause the screen when I get them all up there so you can write them in your notes. Product property. If you have the log base a of a product, x times y, you can split that up into 2 logs. Log base a of x plus log base a of y. Quotient property. If you're dividing, you can split that up to be subtraction. power property, if you have an exponent, you can bring that all the way out front. And so you no longer have an exponent, but remember this goes both directions. Sometimes if we have our exponent out front, sometimes we want to bring it up into the exponent position. So those will go back and forth, and the same thing with product property and quotient property. Be able to go both directions with it. Log base A of 1 equals 0, which makes sense because we think of this in exponential form. This is saying A to the 0 equals 1. Anything raised to the 0 power is 1. Log base A of A equals 1. Again, that makes sense because it's saying A to the first equals A, which is true. Okay, so let's use these properties of log. So right now we're using a quotient one. So quotient property said we could split it up with subtraction. So this becomes log base 9 of 15 minus log base 9 of 7. So we can split that up into two separate ones and solve from there if we needed to. We had log base A of the cube root of m squared. So this one, let's rewrite it with a rational exponent rather than using that radical. So this is really m to the 2/3. Right? Because I have that exponent there, I can bring that out front with my properties of logs. And then this will be log base A of m. So that was using our power property or exponent property. Now, if we're giving a more complex log that we can write as a single log. So this only works when you have the same base. So these all have a base of 3. If you had a different base, let's say two of them were 3 and one of them was 2, you can't take the 2 in conjunction with the 3. You can only combine ones that have the same base. First off, I'm going to take this addition piece and rewrite this as multiplication. So this is log base 3 of x plus 2 times x minus log base 3 of 2. Well, with subtraction now, I can write this as a quotient. So this will be x times x plus 2 all over 2 as one single log. So this is as far as we could go, but we could write as one single log. So take a look in Math Excel, 4.3 day 2. This is going to be due, it's actually going to be due Sunday, 3/22 by midnight. And I'm going to put up one more video for 4.4, and that will be it for this upcoming week of 3/16.